Our goal is to check the convergence and divergence of the following series, the summation of 1 plus 1 over n to power 2 e to power negative n. So it's easier for me to use limit comparison test here. It is easier for me to use limit comparison test here. Why is that? Because from this series, I recognize e to power negative n, and I know the series e to power negative n is basically a geometric series, Remember the behavior of this series. The summation of 1 divided by e to power n can be written as the summation of 1 over e to power n. The ratio here is r, or 1, divided by e. E is Napier number, which is approximately is 1 divided by 2.7182, and so on, which is going to be a small number. This is a less than 1. So I know that this geometric series is convergent. So it is convergent series, this geometric series. So that's why I want to use the limit comparison test. So let's take a look at my series here. The general term, as you can see, is 1 plus 1 over n to the second power e to power negative n. The limit of this series, the general term, right? We're taking the general term of this series. Limit of 1 plus 1 over n to power 2 e to power negative n divided by e to power negative n as n goes to infinity. So let me use a different color for this guy. I'm using the geometric series general term e to power negative n as n goes to infinity. But quickly note that you can cancel out these two common factors. So you end up with the limit of 1 plus 1 over n to power 2 as n goes to infinity. But this guy, 1 over infinity, is 0. So you end up with 1 to power 2, or just 1. Since 1 is a finite and positive number, the limit comparison test tells me that the convergence and divergence of the series of 1 plus 1 over n e to power negative n, n starts from 1, goes to infinity, and the second series, the summation of e to power negative n, n starts from 1, goes to infinity, are the same. But since we know that this geometric series is convergent, it means that the other series must be convergent as well. Since the series e to power negative n, n starts from 1 to infinity, is a convergent geometric series. So the series of 1 plus 1 over n e to power negative n starts from 1, goes to infinity, is also convergent. So let us recap what we did. We have the series of 1 plus 1 over n to the second power e to power negative n, and we want to check the convergence and divergence of this series. Again, it's easier for me to use limit comparison test. Why is that? Because I recognize e to power negative n here. So this is my very first step. My first step is to recognize something that is familiar to me, like e to power negative n, or a p series, something that helps me to simplify this a little bit more. We know that the summation of e to power negative n is a geometric series. It can be written as 1 over e to power n. So the ratio is 1 over e, and it is less than 1. So based on the test for geometric series, it is a convergent series. Now, using the limit comparison test, if you assume this is your an and this is your bn, and you do the limit of an over bn as n goes to infinity, you can cancel out e to power negative n. E to power negative n get canceled out, so you end up with the limit of 1 plus 1 over n to the second power as n goes to infinity, but this guy is nothing but 0, so you end up with 1 squared or just 1. Based on the limit comparison test, since 1 is finite and positive number, it tells us the series, both of them are both convergent or both of them are divergent. But since the geometric series is a convergent series, you for sure can say that, hey, my series 1 plus 1 over n, e to power negative n starts from 1 to infinity is also convergent. There's a common mistake for students on the exam that we see frequently. The common mistake is that students confuse this test with ratio test. Students confuse the limit comparison test with the ratio test. Remember that for the limit comparison test, when you're finding the limit of an divided by bn as n goes to infinity, and you end up with c, which is a positive finite number, then the convergence and divergence of series are the same. Convergence and divergence of series an and series bn are the same. The common mistake that students have saying that, okay, since we have 1 here, it means that the test is inconclusive. Then students write, since the limit is 1, the test is inconclusive. The test is not working, or it is inconclusive. They confuse the limit comparison test with the ratio test. Remember that in the ratio test, we had the following case. In the ratio test, we take the limit of absolute value of an plus 1 divided by an as n goes to infinity and this guy is equal to L. If L is less than 1, you have convergence. If L is more than 1, you have divergence. And if L is equal to 1, you said that the test is not working. Test is not working. It means that we have to move to a different method, a different technique, or different test. So students confuse these two. Limit comparison test, you have two tests, two series and two general term to work with. And if the limit of the quotient of those two general terms is equal to a positive finite number, then the convergence and divergence are the same. For the ratio test, however, you have the same general term in the form of n plus 1 and n. So you're taking the ratio of the general term in consecutive terms and finding the limit. If the limit is equal to 1, the test is not working, inconclusive. So it's a common mistake on the exam that we see students taking these limit and they say, hey, the test is not working here, it's not correct. If you're using limit comparison test, please be careful, do not confuse it with ratio test.